All right, so no quote of the day today. We're just going to jump right into it. The plan for today is to cover 11.8 power series and possibly start into 11.9 on representing functions as power series. Uh, so sorry, today my allergies are really acting up. I was working outside a bunch this past weekend with the nice weather and everything, and between that and the springtime and all of that, I might have to pause a couple of times to blow my nose or something. But okay, so before we jump into power series, just kind of in a couple of notes. The first note, I posted the flow chart for, let me actually just bring it up here. I posted the flow chart for series convergence tests. This is something that somebody from University of Hawaii published, and I think it's just the best one of these that I've seen. I tried to make one myself, and I was like, why am I going to reinvent the wheel? This one is quite good. So this just goes through a flow chart of the different possible tests. Tests for divergence, super easy to do. Do the individual terms limit to zero? Going through P series, geometric series, alternating telescoping, Taylor series, which we'll see coming up fairly soon. And then just a list of the different other tests that we could do. We recognize like the ratio test, integral test, and so on. So that's posted on Blackboard. You can take a look at that. And then a couple other series properties that we can use. If we have two series that both individually converge, then they kind of the summation operator kind of acts like a linear operator. Constants can come out, and the summation operator can break up sums. Note that we have to be careful. It's not true the other way around. If the series of the sums of the individual terms converges, then we don't necessarily know that each of the kind of broken apart series necessarily converges. We could imagine something like an is +1 for all n and bn is -1 for all n. Well, of course, the sum of a whole bunch of zeros is just zero, but some +1 or some -1 both diverge. So we could have two divergent series that when we kind of glue them together term by term become convergent. But if we have two series that are convergent individually, when we kind of glue them together term by term, they'll still be convergent. We can also say that if we have one convergent series and one divergent series, and we kind of glue them together in a sense term by term, then that combined series will diverge. So these are some helpful properties, particularly these two up here I find to be quite helpful. We know that we have to be very, very careful applying even very basic algebraic techniques to infinite series. And this gives us a few algebraic techniques that we can apply to infinite series, again, provided that we know that they converge. All right, so 11.8 on power series. So what is a power series? A power series is a series of the form sum n equals 0 to infinity of c sub n x to the n. We take x to the 0 to be 1. So this is c naught plus c1x plus c2x squared plus c3x cubed, and so on. Or sometimes we choose to write this as sum n equals 0 to infinity of c sub n times x minus a to the n. So c naught plus c1 times x minus a to the first plus c2 x minus a to the second, and so on. We would call this a power series centered at a. And if we wanted to be, to give a little extra information, we might call this a power series centered at 0. So we can see, for instance, that sum n equals 0 to infinity of x to the n is a power series. That's just where all of our coefficients are 1. We note that the sum of this series is a function f of x, and the domain of that function is going to be the set of all x for which the series converges, for which the sum exists. So where does this series converge? For what values of x does this series have a sum? For what values does the series converge and have a sum? Of course, that's the open interval -1 to 1. We recognize it's in a slightly different form, but we recognize that this is just the geometric series when my initial constants are all 1. And I know that a geometric series converges when its ratio, when the base, is strictly between -1 and 1. So this series, sum n equals 0 to infinity x to the n, is a power series with domain the open interval -1 to 1. We have a super helpful theorem for power series. This is going to essentially come up in, I suppose, basically every problem. For a given power series centered at A, exactly one of the following is true. Option 1, the series converges only at x equals A, and the domain is just the single number A. Note that a series always converges at its center because we have C naught plus C1 times x minus A. Well, when I plug in x equals A, that's 0. X minus A squared is 0, x minus A cubed is 0, and so on. We see that the nth partial sum is always just going to be C naught. And of course, that sequence consisting of just all of the elements are C naught will just be that constant. So power series always converge at their center, but it's possible that a series could converge only at its center, nowhere else. It's also possible the series converges for all x for all real numbers. I mean, I suppose we could look at a goofy series where like C1 is 1 and all of the other CIs are like 0 or something. It could converge for all x for all real numbers. The domain could be all real numbers. Or the third possibility is there exists r bigger than 0. There exists a radius of convergence, we call it, a positive number, positive real number, such that the series converges for absolute x minus a less than r and diverges for absolute x minus a bigger than r, and may or may not converge at the endpoints. And the note down here, so it might kind of, at a first glance, it might seem like we didn't really say anything. It might seem like we said the series can converge at one point, the whole real line, or kind of anywhere on the real line. But note that we actually did say something really strong here. We said that a power series converges on a symmetric interval about its center. That interval might be of width 0, being just at the center. It might be of width infinity or radius infinity, being the whole real line, or it might be on some non-zero, non-infinite symmetric interval. But if our series is centered at 0, we can't like only converge on the open interval like -2 to +7. That's not symmetric about 0. Our power series converges, or its domain is a symmetric interval about its center. So we actually did make a pretty strong statement here, even though maybe at first glance it seems like we might have said not very much. So again, the radius of convergence is what we call this number r here. And if we kind of expand our view a little bit to 0 to infinity, we can think of line 1 kind of being like a radius of convergence of 0, and line 2 being like a radius of convergence of infinity. Okay, so this is the really important point here. The power series converge on symmetric intervals. And as I mentioned, these intervals could include neither one or both endpoints. So 4 different possibilities for the endpoints convergence. Could converge at the left but not the right but not the left, neither or both. So what the typical process would look like, typical procedure would be to find the radius of convergence and then check each of the endpoints individually, just those two special cases. Okay, so let's look at this series. So consider sum n equals 1 to infinity of x to the n over n to the p. Find the radius of convergence in the interval of convergence. Okay, so let's work through this. Now, something that we might notice is that we have these x to the n powers here. And what I want to know is when I plug in a value for x, in essence, do my terms blow up or do they get small really fast? If I think of my terms of my series as being like x to the n minus 1, x to the n, x to the n plus 1, I see that there's a very natural progression of the x's where each next term has one extra power of x. And I'm really interested in what happens to these x's. This is really just kind of screaming for the ratio test. And essentially all of these power series, that's where we start. We start by setting up a ratio test. So I start by looking at absolute value of, let me call each of these a sub n, an plus 1 over an, and then I know that I get convergence when this is less than 1. Or this is absolute value of what? X to the n plus 1 over n plus 1 to the p times n to the p over x to the n. My n to the p stuff is all positive. X to the n plus 1 over x to the n just leaves me with x. I have to be careful. I still have my absolute values on the x, but the n stuff can all come out of the absolute values. And what happens to this as n goes to infinity? This goes to absolute value of x. And my ratio test says the following. It says, if this is less than 1, I'll write it over here. If this is less than 1, I converge. And I actually converge absolutely. If it's bigger than 1, I diverge. So we're kind of starting to see why this nice kind of like symmetric interval thing has to happen. And if it's equal to 1, it's inconclusive. In other words, at the endpoints that border between convergence and divergence, our ratio test is inconclusive, so we have to use something else to assess the convergence there. So my radius of convergence is 1 because absolute x less than 1. If I had come over to here and had absolute x over 3, then when I solve for absolute x, I'd have absolute x less than, since it was absolute x over 3, I multiply both sides by 3, absolute x less than 3. And then that would tell me that my radius of convergence would be 3. So when I get absolute x less than something from the ratio test, that gives me my radius of convergence r. And this tells me that I converge on, well, my center is 0. This is like x minus 0 to the n. I converge on open minus 1 to 1 definitely. I diverge on minus infinity to minus 1 open and 1 to infinity open. And I'm not sure about minus 1 and plus 1. So I don't know whether like this should have 2 square brackets or 1 square bracket or what. So I'm going to check those individually. But this is what I found out so far. I've knocked out most of the real line, just 2 special cases to check. If we check x equals minus 1, what is our series then? Sum n equals 1 to infinity of minus 1 to the n over n to the p. This is an alternating series. And well, what does that mean? As an alternating series, if my terms are non-increasing and go to 0, then I converge. So 1 over n to the p non-decreasing and limits to 0, When does that happen? When p goes, or when p is bigger than 0. My other special case was x equals +1, which give me some n equals 1 to infinity of 1 to the n over n to the p, or just 1 over n to the p. Well, this is a p series. Converges if and only if p is bigger than 1. We have 3 different scenarios here. If p is less than or equal to 0, we converge on open -1 to 1, and that's it. If p is bigger than 0, but less than or equal to 1, we converge at the left endpoint, but not at the right endpoint. And if p is bigger than 1, we converge on the closed interval -1 to 1. We see that symmetric region in all 3 cases, and this kind of p series, this exponent p in the bottom here that we know has an effect on convergence, really only affects that convergence at the endpoints, not on the interior of the radius of convergence, and it doesn't, change divergence on the exterior into convergence or anything like that. It's just the endpoints that it affects. Okay, let's look at something like this. Some n equals 1 to infinity of x to the 2n over 2n factorial. Find the radius of convergence and the interval of convergence. Just like before, let's call these an. We set up our ratio test, absolute an plus 1 over an. This gives me x to the power, let me be careful here. 2 times n plus 1 is 2n plus 2. A little tempting to write just 2n plus 1 up there. Over 2n plus 2 factorial, same thing here. Times 1 over an is 2n factorial over x to the 2n. I see all of my x's are going to cancel except 2 on the top. So I have absolute value of x squared, or I really can get rid of the absolute values at this point if I wanted to. I have 2n factorial over 2n plus 2 factorial, but 2n plus 2 factorial is 2n plus 2 times 2n plus 1 factorial, which is 2n plus 1 times 2n factorial. So these are going to divide out, leaving me with 2n plus 2, 2n plus 1 on the bottom. Remember that x is is some fixed real number, and n is the thing that's moving. N is the thing we're taking the limit of. The limit as n goes to infinity in the ratio test. For whatever fixed real number x is, absolute x squared is just some fixed real number. But this 1 over 2n plus 2 times 2n plus 1, that bottom is getting larger and larger. This is all going to 0. This can be a little confusing to interpret. What does this mean? Does this mean our radius of convergence is 0 or what? Well, no, what this means is that pick any real number x. It could be 1,000,000 or 1,000,000,000 or -100 million, whatever. Pick any real number for x. Run the ratio test. This ratio goes to 0. This is a real number less than 1. This implies that we're absolutely convergent for any real number x. My x's all went away, and I was left with a number that is less than 1 from the ratio test, regardless of what x was. This converges regardless of x. This converges for all real x. My radius of convergence is infinity, and I converge on minus infinity to infinity, or my interval of convergence is minus infinity to infinity. Right. Another way to think about it is that the numerator kind of grows exponentially, the denominator grows factorially, and k factorial kind of looks like k to the k. So if I'm growing exponentially on top, but like super exponentially on the bottom, that seems like that's going to zero pretty quickly. I mean, that's not a proof, but that's just kind of like a heuristic. What about this one? Sum n equals 1 to infinity of x minus 1 to the n power over n. Again, find radius of convergence and interval of convergence. Just like before, we start off, well, we might note here that the center x minus a to the n is, the center is 1. So let's make note of that. And we start our ratio test. We call these an. So absolute an plus 1 over an, or times 1 over an. Like usual, all of our powers of x go away except basically one of the powers. So we're left with absolute x minus 1 times n over n plus 1. What happens to this as n goes to infinity? Turns into just absolute x minus 1. And then our ratio test says if this is less than 1, we converge absolutely. Bigger than 1, we diverge. Equal to 1, inconclusive. So we converge for absolute x minus 1 less than 1. That is to say that we converge for negative 1 less than absolute, or not absolute, less than x minus 1 less than 1, which is to say that we converge for 0 less than x less than 2. Right, we had a radius of convergence of 1 around the center of 1. So we converge from 1 minus 1 to 1 plus 1, or from 0 to 2. We diverge when absolute x minus 1 is bigger than 1. So that's when x less than 0 or x bigger than 2. And again, we don't know about the endpoints. We have to check those individually. So let's check x equals 0. If I plug in x equals 0, I get negative 1 to the n over n. And I recognize this as the alternating harmonic series, which does converge. If I look at my other endpoint, x equals 2, put in x equals 2, 2 minus 1 is 1. So that's 1 to the n, or just 1 over n. This is the harmonic series that diverges. I converge at 0, diverge at 2. So again, my center is at a equals 1. My radius of convergence is r equals 1. And my interval of convergence is 0 to 2, include 0, don't include 2. So closed 0, to open 2. Again, symmetric interval of convergence about 1. Again, plus or minus the endpoints. We did converge at 0, not at 2. Okay, so any questions so far? So that ratio test really is key to this section, or really this just general topic, the next several sections. So example 4, one solution to this Bessel's differential equation that's quite complicated to solve, which is why the solution looks so messy, is given by this power series. We talked a little about differential equations earlier in the course. And when we're solving differential equations, we often have nice solutions like exponentials or sines or cosines, things like that, and that works pretty nicely. But if I look at the class of all functions that could be written nicely as, polynomials, like finite polynomials, exponential, sines, cosines, power functions, these kinds of things. If I expand my view to a larger class of functions, specifically those functions that can be written as a power series, this is actually a larger class of functions. I can write exponential functions, which we'll see in a bit. I could write exponential functions as power series, sines and cosines as power series, and so on. But I could also write other functions as power series. So if I actually search for power series solutions to differential equations, I have, in some kind of loose sense, a better chance of finding a solution. There might be a solution that exists in the kind of edges of functions where you can only represent them as power series and not nicely as exponentials or trig functions or whatever. So it turns out that this power series is a solution to this differential equation. We're not going to go through and prove that or anything like that, but just to show you where this series comes from. So in a full diffie class, you would spend some time on power series solutions to differential equations. So that's where you might encounter something like this. We see there's a power of x in front here, but that doesn't do a whole lot. What I'm really interested in is this series. And in particular, I see that I have x to the 2n over some n factorials. I know those n factorials in the bottom grow really quickly, and this numerator grows exponentially. The denominator is going to grow super exponentially. I think this is going to converge, probably for like all real numbers. Let's go through and check that carefully. Let me just pop that x on the inside. So this is my an. I notice that my center a is 0. So that's something maybe worth noting. Sorry that we have a's and an's for the center in the kind of typical term. My ratio test, I write absolute an plus 1 over an. I know I'm in an absolute value here. I'm just not going to write the negative ones. That's just going to clutter things up. So 2 times n plus 1 is 2n plus 3 over 2 to the power 2n plus 3 n plus 1 factorial n plus 2 factorial. So that is an plus 1, getting rid of the minus 1 to the n, because again, we're in absolute values, so we'll just knock that off. And then I need times 1 over an, so that puts in x to the 2n plus 1 on the bottom. 2 to the 2n plus 1 n factorial, n plus 1 factorial on top. And we get massive cancellation, right? Let's see, what can I do first? Well, let's do the x's first. I notice everything else is positive, so I'll do the x's inside of the absolute value and pop everything else out. I have an x squared. This would be inside the absolute value, but I also just note that x squared is non-negative, so I can actually just get rid of the absolute values from there as well. So typically I would have absolute values around my x bits, but I don't even really need them here. That takes care of the x's. I have 2 powers of 2 on the bottom, so this is going to be, let's just write it as an over 4. My n plus 1 factorials actually both go away. N factorial over n plus 2 factorial, I think that's going to be an n plus 2, n plus 1 on the bottom times an n factorial, so I think I've got those taken care of, and then 1 over that. Very similar to what we saw a couple of examples ago. And again, as n goes to infinity, what do we get here? As n goes to infinity, remember, x squared is, it can be any real number that we're testing, but it's a fixed real number. Even if it's 100 billion, it's a big real number, but n is going to infinity. This x squared is a fixed real number. This is all going to 0, which is always less than 1. So it converges absolutely, regardless of which real number x we choose. Large positive number, large negative number, number close to 0, doesn't matter. Still limits to 0, less than 1, still converges absolutely. So my center is 0. My radius of convergence is infinity. This is one of the special cases where I kind of expand my view of radius of convergence, and my interval of convergence is all real numbers. The domain of this function is all real numbers. So that's pretty nice. It looks like anyway that I've solved my differential equation on the whole real line with this solution. Any questions so far? Give me 1 sec real quick. Okay. So moving on to example 5. Here we have the series sum n equals 1 to infinity of n factorial times x to the n. Now, again, we know that n factorial grows pretty quickly, and here it's in the numerator. So, I mean, if x to the n, if x is a number outside of minus 1 to 1, x to the n is going to get big. It's not going to get close to 0. And n factorial is going to get big as well. Like, we can pretty clearly see right away that if x is not n minus 1 to 1, this is definitely going to blow up, right? Test for divergence would show that. But it kind of seems like even if x is in the interval 1 to 1, like a half or something, x to the n is getting small exponentially, like 1 over 2 to the n, but n factorial is getting big super exponentially. I'm not so confident that this is going to converge even if x is a number pretty close to 0, pretty close to its center. But let's look through this carefully. Okay, so we see that we're centered at a equals 0. Let's note that. We'll call this an, n factorial x to the n, and we'll set up a ratio test. I note that n plus 1 factorial is n plus 1 times n factorial, or is just n plus 1. Absolute x to the n plus 1 over x to the n is just absolute x. And I want to know what happens to this as n goes to infinity. X is some real number. So if x is a number like 2 or negative 20 or something, n plus 1 multiplied by that as n goes to infinity. This goes to infinity essentially for all x. The only place that this limit doesn't go to infinity, and this is a little tricky, we have to remember kind of what order we're doing things in. This goes to infinity if x is not 0. But if x is 0, if I'm analyzing this series for the specific case where x is 0, that specific real number, then when I get to here, this is just 0, which of course limits to 0. For any real number x that's not 0, that's not right at the center of the series, my ratio shoots off to infinity, which of course is bigger than 1. My ratio test says we diverge. We diverge for any x, for any input that's not 0. We converge at and only at the center of the series when x equals 0. So my center, a equals 0. My radius of convergence, I converge on an interval of width 0. And my interval of convergence is not really much of an interval at all. It's just the singleton 0. Now, so a minor detail of note, the center of the series and the location of convergence are tied together. Those two zeros are like, in a sense, the same 0. We converge at 0 because the center is at 0. The radius of convergence being 0 is kind of a different 0 in a sense. In other words, just to give an example, sum n equals 1 to infinity of n factorial x minus 3 to the n. If we looked at this instead, this would have center a equals 3. This would have radius of convergence still r equals 0. That's how far I go to the left and right of 3 to get my interval of convergence. I go 0 units to the left or right. And my interval of convergence would be the singleton 3. So it's not like my radius of convergence would become 3. My radius of convergence is still 0. That's the kind of, well, half the distance on the real line from the left to the right endpoint of interval of convergence. But I converge at the center with 0 radius of convergence, so my interval of convergence is just 3. Any questions so far in this? Okay, let's keep going. And as an aside, we're also getting some practice on our previous series work here too, right? When we have to check these endpoints, which we haven't had to do in a couple of problems before that, when we had to check the endpoints, we were getting practice on other tests for convergence. So here we have sum n equals 1 to infinity, x to the n over n times 3 to the n. Radius of convergence and interval of convergence, let's check. Okay, so my center is at 0. I'm going to note that. Absolute an plus 1 over an is absolute x to the n plus 1 over n plus 1 3 to the n plus 1 and times 1 over an. So n times 3 to the n over x to the n. Most of my x's go away, so I end up with x to the 1 inside the absolute value. That takes care of those two factors. I have an n over n plus 1. That takes care of those. And then I have a 3 to the n over 3 to the n plus 1. That's a 1/3. So I think that should take care of everything inside those absolute values. And what does this limit to as n goes to infinity? This limits to absolute x over 3. And again, my ratio test says if this is less than 1, I converge, bigger than 1, I diverge, equals 1, inconclusive. Or in other words, I can multiply through by the 3. If absolute x is less than 3, I converge. If absolute x is bigger than 3, I diverge. Absolute x equals 3, I'm not sure. So I converge, or for x in minus 3 to 3, I diverge on the open interval outside of that, and I have to check minus 3 and plus 3. Right, so here I have a radius of convergence of 3. So we haven't seen a radius convergence that's not 0, 1, or infinity yet. This is how we would get one of those. If we have, like, this kind of has the feel of like a geometric series a bit, right? Like x over 3 all to the n. Okay, let's check these two special cases. X equals -3, we're investigating the series. This would be -3 to the n. And I'm actually just going to rewrite it as 1 over n, x over 3 to the n, like that. So sum n equals 1 to infinity of, if x is -3, I see this is -1 to the n over n. That's the, I guess it's not technically the alternating harmonic series. It's negative the alternating harmonic series, but this is basically the alternating harmonic series, which converges. And then for x equals +3, sum n equals 1 to infinity of 1 over n times 3/3 to the n, or just 1. This is the harmonic series. It diverges. So we diverge at the right endpoint, we converge at the left endpoint. My center, a equals 0. My radius of convergence was 3. And my interval of convergence, -3 to 3. I converge at the left endpoint, diverge at the right. And again, this would close -3 to open 3 would be like the domain of my function, where that function is the sum of this series. Those are the x's I can plug in and get a sensible sum out of that function. So that will be the domain of my function. Any questions so far? Okay, so another example. Consider the series sum n equals 1 to infinity of -2 to the n over root n times x plus 3 to the n. Same questions as before. Remember, I want x minus a to the n for my center, so my center is, is -3. And as before, I start by setting up my ratio test. Here's my an. I know everything's going on inside absolute values. I'm just going to knock off that negative sign, I suppose. So 2 to the n plus 1 over root n plus 1 times x plus 3 to the n plus 1. That's absolute value of an plus 1. And then 1 over absolute an, which would give me a 2 to the n on the bottom, or root n on top, and an x plus 3 to the n on the bottom. All right, so 2 to the n plus 1 over 2 to the n, that gives me a factor of 2 that can come out. That takes care of those ones. I have a root n over root n plus 1. Those are both positive numbers. They don't need absolute values on them anymore. And then I have absolute x plus 3 left over. And again, I ask what happens to this as n goes to infinity. This becomes 2 absolute x plus 3. Right, the root n over root n plus 1 goes to 1. And then I say if this is less than 1, converge absolutely, bigger than 1, diverge, equals 1, inconclusive. Or I could go through and I could divide through by 2. My radius of convergence is 1/2. So I converge on the interval absolute x plus 3 less than 1/2, or the interval centered at -3 going half a unit either way. I converge on -3 minus 1/2. That's what, -7/2 to -3 plus 1/2. That's -5/2. I diverge on kind of the open complement, minus infinity to -7/2, union -5/2 to infinity. And I have to check my endpoints. Maybe instead of putting a comma, I'll put in and. Let's check these two endpoints. So when x is -7/2 or -3.5, give me 1 sec. I even took a double dose of Allegra today, and because of all the spring and all that, and probably helped a lot. But anyway, so looking at x equals -7/2 or -3.5. Can I get all of this on the screen? So I'm looking at the series sum n equals 1 to infinity of -2 to the n. Being careful to keep that negative sign here. That's important at this point. I just got rid of it just for that ratio test calculation. Over root n times Well, negative 3.5 plus 3 is negative 1/2 to the n. Or this is 1 over negative 2 to the n times 2 to the n. This is sum n equals 1 to infinity of 1 over root n. Or we could think of this as sum n equals 1 to infinity of 1 over n to the 1/2 power. Seems like 1/2 is like the theme of this this problem. We of course see this as a p series, and in particular it's a p series with p less than 1. P series only converge when p is bigger than 1, so this diverges. It's a p series with p not bigger than 1. If you can read that says series, p series with p not bigger than 1, so we diverge. We diverge at the left endpoint. What about at the right endpoint? X equals negative 5/2, or in other words, negative 2 1/2. So what do we get? Negative 2 to the n over root n. Times x plus 3 to the n. Negative 2.5 plus 3 is plus 1/2 to the n. Negative 2 to the n is negative 1 to the n times 2 to the n over 2 to the n. This is sum negative 1 to the n over root n, and those 2 to the n's went away. Well, this is an alternating series. And I note that 1 over root n is a decreasing function. It's non-increasing and limits to 0. An alternating series whose absolute values of the terms are non-increasing and limit to 0, this converges by the alternating series test. I converge at the right endpoint, not the left endpoint. So kind of in summary, I'll come back up here where I had my stuff all written. So in summary, my center was negative 3. My radius of convergence was 1/2. And my interval of convergence was from negative 7/2 to negative 5/2. I diverge at the left endpoint, so I don't include that. I converge at the right endpoint, so I will include that. Or this interval, open negative 7/2 to close negative 5/2, is the domain for my function. Any questions so far? Okay, let's maybe skip this one. And for these, I don't know why the numbering restarted, but let's look at these next 4. And then we will come back to this one kind of as a warm-up next class, and then jump right into representing functions as power series. But let's take a look at these 4 problems here. So suppose we can say that sum n equals 0 to infinity of Cn x to the n converges for x equals negative 4 and diverges for x equals negative 6. What can we say about these 4 series? So we have a series that has center a equals 0, x minus 0 to the n. It converges at negative 4. So if I think of a number line, here's my center at 0. At negative 4, we converge. And at negative 6, we diverge. I know my radius of convergence has to be at least 4, but no more than 6. Or maybe I'll write it a slightly different way. I feel like that's maybe a little bit misleading to write it that way. No more than 6, but at least 4. I don't want us to get the interval 4 to 6 confused with the number line over there to the right. Or my interval of convergence can be as small as kind of open -4 to +4, but then include the left endpoint and who knows about the right endpoint. Or it could be as large, whoops, that should be an X. It could be as large as open -6 to +6, do not include the left endpoint and who knows about the right endpoint. So what about X equals 8? Well, 8 is over here on the right side. It's 8 units to the right of 0. If we converge there, we would have to also converge at -8 by symmetry. -8, it could be at the endpoint, but we'd have to converge at least kind of up all the way up to -8. But we don't converge at -6. We have to diverge here. For -5, what about that? Well, we converge at -4, but diverge at -6. I'm not really sure. Again, our interval of convergence could be like close -4 to something like close +4, where we would diverge to the left of -4 at -5. Our interval of convergence could also be like open -6 to like close +6, where we would converge at -5. It could be really anything in between there. No way to tell. What is this asking? This is really asking, what about X equals -9? But again, -9 is to the left of -6. We have to have symmetric intervals of convergence, right? This has to diverge. What about +4? I know we converge at -4. Does that imply we converge at +4? It's like really, really close to implying it, but not quite. If we converged on an open interval containing -4, then we could say yes. But we could converge at -4 by converging on kind of the open interval from -4 to 4 kind of naturally, and then also converging at that endpoint -4. If -4 is the endpoint, which we don't know, it could be, it might not be. If -4 is the endpoint of the interval of convergence on the left, then +4 would be the endpoint on the right, and it could go either way. So, and because that is a possibility, that my interval of convergence is from -4 to 4, and this is the rightmost endpoint, I don't know. If I knew that my interval of convergence, that kind of that initial open interval contained -4, like I went from -4.5 or -5 or something off to the left, then I would know that I converge at +4. But because I could converge at -4 by having -4 as the left endpoint, I really can't determine whether I converge at +4. Okay. All right. And again, next time we'll come back, we'll do this problem kind of as a warm up leading into representing functions as power series.